I've given you back the test. I haven't looked at the scores carefully, to see what the range is. I know the low score was in the 50s, which is better than it's been on any of the other exams. And the high score is in the mid 90s, which is, a good high score. But the median score, I think, is in the high 60s, and the average score is like 71. So I haven't thought much about, like I said, I haven't really looked at it. That's all I remember about the scores. And so I will be looking at those. I'll be looking at those this afternoon, entering them into Moodle, and any adjustment, if I deem one is necessary, will be reflected then. I'll also make sure I have everything that is graded recorded by this evening, and I will put a spreadsheet on Moodle. I'll actually make a PC version and a Mac version. How many people have Mac computers? Okay, so there's more than one. It turns out Excel does not import web pages the same with the PC as it does with the Mac. So I'll make a spreadsheet that you can then copy your grade report from Moodle, paste it into the spreadsheet. It'll tell you where you stand for your final grade, what score in the final exam would correlate to what change in your grade. So that's something to look forward to this afternoon. Did I have questions? It seemed like I had somebody. Any questions before I get started? Okay, I will also, for anyone who has perfect attendance up to this point, they'll get the attendance bonus added to their Moodle grade today. Perfect attendance means you haven't been late to one lecture all semester. I don't know. So,
with the exception of like the 2 or 3, right?
Well, perfect attendance now means you've gotten the bonus. Next week, by the time we get to the end of next week, then it'll be with those, right? Because you can miss all of next week if you have perfect attendance today.
Even one target, you don't get it.
You don't get it right now with one target. At the end of next week, if you only had one target, of course you'd get it. Right. So I just don't want to put it in assuming, and then you say, I got it, I'm not coming to class. Okay. In class on Wednesday, I worked really hard and didn't say Wednesday. We studied periodic motion. We learned about period frequency and angular frequency, and the requirement that a simple harmonic oscillator has a linear restoring force. What does it mean for it to be a restoring force first? What does restoring force mean? Okay, restoring force means that it is a force that brings it back. So restoring means the force is negative something, linear, proportional to how much you've displaced it, and then the K, because it's a constant, which we call the spring constant. So in your homework problems, one of the things you have to do is calculate the spring constant. You have this much force causes this much stretch. How do you find the spring constant? Yeah. If you just divide both sides. Now, taking it out of vector to a linear equation, we also usually drop the minus sign because it's telling you the direction only. And we just say, well, force equals kx. We divide both sides by x. Then we have k. So k is just force over x. Spring systems. I have 2 springs here. Were examples of a simple harmonic oscillator. And we learned that for a spring system, we have the angular frequency is square root of k over m. So it has to do with how much mass is oscillating and what the spring constant is. Now with a pendulum, there is no spring, right? But it has a restoring force, and that restoring force is approximately linear. Remember, for simple harmonic oscillation, it has to be a linear restoring force under one special condition. What's the special condition where the restoring force for a simple pendulum is linear with displacement? Small angle. So for small angles, a pendulum behaves like a simple harmonic oscillator. And for the pendulum, Yeah, you have omega is equal to square root G over L. And so it doesn't matter what the mass is for a pendulum. It's going to have the same period whether it's a low mass or a large mass. It matters what the length of the pendulum is and what the acceleration of gravity is. Now, I forgot, I want to talk about one thing on the test, a couple things. First thing is units. A lot of people missed points because they didn't convert units. For instance, there were people who tried to use Fahrenheit units in the ideal gas law. It has to be absolute temperature units to use the ideal gas law because it's not a change in temperature, it's a temperature.
So
And so, another one that people missed points on because of units was I think it's number 21, I just looked at before class with the student, where you are, again, utilizing the ideal gas law, but you have to use P and V in the units that match your R. Randy?
Should we just always switch it to Kelvin? Because there's no real downside.
Right. There are very limited special cases where you can't switch it to Kelvin. So pretty much always switching to Kelvin is safe. Finally, I have to point out, I put in a historically factual problem there about deflate gate. In fact, if you look on your rubric sheet, it called it deflate gate. The temperature of the air when they blew up when they measured the pressure in the footballs before the game would have had to been 120 degrees or higher for the footballs to have not leaked and been properly inflated before the game. New England Patriots, their excuse is our air compressor compresses at 130 degrees Celsius. That was their excuse. But think about how hot 130 degrees Celsius really is. It's very, very hot. It's well above the boiling temperature of water. I tend to not even believe that their compressor is, doing that, but that was their excuse. Moving in to the lecture. I wanted to start with a couple of problems. A mass of 1.2 kilogram at the end of a horizontal spring of spring constant 140 newtons per meter on a frictionless horizontal surface. Notice this is horizontal. Anyone want to guess why it's horizontal? To make it easier because you don't have to think about gravity. If you do it vertical, you actually get exactly the same results. It's a little more confusing when you have to think about gravity. So that's why it's horizontal, but it's a frictionless surface, so it just goes back and forth. The block is pulled and stretched a spring distance of A equals 9.5 centimeters from equilibrium. What do we call this number here? The A is there for a reason. No answers? It's because the amplitude is the name for the maximum displacement. And it goes from plus A to minus A. So here's a graph of what the simple harmonic oscillations look like for this problem. And it tells us the amplitude here is 9.5 centimeters from equilibrium. And it gives us the mass. Write an equation for the angular frequency omega. This is really tough because what did I just write in the previous slide? What is omega? And don't forget the square root, David. Yes, I know, but it's not what you did.
Earlier.
So that was not hard at all. What is K? K is given. What is M? M is given. And so then you calculate by putting the numbers in. What units are you going to get when you put those numbers in? Well, let's expand it out. Okay, 140 over 12. What's 140 over 12? It's a little less than 12, obviously, because 144 would have been 12. Well, would have been 120.
11 and 2/3.
It's what?
11 and 2/3.
Okay, a Newton is a kilogram times meter per second squared. Notice meters, oops, that was kilograms on bottom. This was per meter there. These meters, the newtons per meter makes those meters cancel. The kilograms on bottom cancel with the kilograms on top. And so I'm left with square root of 11.67. What's that? Since you have 11.67 in your calculator. And then square root of 1 over second squared. Tell me why I'm wrong.
Square root should get rid of seconds.
The 1 over second square root is 1 over seconds, right? And hertz is 1 over seconds, right? But this is actually angular units of radians per second. You have to be careful with that because radians per second are technically the same units as hertz. But the difference is one is measuring angle per time and one is measuring cycles per time. So you have to know that when I'm doing that square root K over M, my units are radians per second. This is angular frequency. Whereas if I had done frequency is equal to omega over 2 pi. 2 pi is in radians. The radians cancel, even though radians are unitless, and that would give us the frequency in hertz. So there's confusion that you need to make sure you have clear in your head so you don't make mistakes just based on units. Any questions about this right here? Okay, write an equation for the period. That's not hard. What's the relationship between period and frequency?
1 over frequency is 1 over period.
So period is 1 over frequency, which means it's 2 pi over omega, which means it's 2 pi square root m over k. That's not hard at all.
Yeah, man. That's cool.
And then you calculate the period. Well, since we've already calculated omega, we would just have 2 pi divided by 3.42 rads per second. I'm not even going to waste my time. Write an equation for the maximum speed. Now, this is something we haven't studied. It's something that comes up 2 slides from now. Maximum speed. To get to the maximum speed, we look at energy. So we have a spring system, and when it was released, it was stretched out, so you had an amplitude of, in my case, I think it was 9.5 centimeters. And it's stationary when you release it. So what's the total energy initial? What's the kinetic energy if it's stationary? What's the potential energy?
Maximum.
It is maximum. If it's a spring, it's 1/2 the spring constant times the amplitude squared. So that's the initial energy. Now, if there is no friction, because the problem stated it's a frictionless system, then what's happening to the energy over time? It's constant, because there's nothing to take away energy. It has no non-conservative forces. So then we say, okay, what about when it's at its max, its x equals 0 position? So let me call this E1 instead of E initial. What's the equation for kinetic energy when it's at its center position? You don't know its speed, right? So what's the equation for kinetic energy? It starts with 1/2. Kinetic energy. 1/2 m v squared. Thank you, Diana. So there's the kinetic energy. If the spring is unstretched, what's its potential energy? 0. But since there's no conservative forces, these have to equal each other. Now notice this is going to be the fastest possible speed because kinetic energy cannot be negative. So when kinetic energy is 0, you have all of your energy in, or excuse me, spring energy also cannot be 0. So when spring energy is 0, then all of your energy is in kinetic. It's the maximum it can be. So this is going to be the case that gives me my maximum speed because the potential energy was 0. And so now I can solve this right off the bat. 1/2 k times the amplitude squared equals 1/2 m times the maximum speed squared. All of you being good mathematicians, what would you do first? Multiply by 2. There's no reason to keep those 1/2s around. Since I'm looking for v, I'm going to divide everything by m. And then I square root this baby. Square root this baby. Now notice there's two answers. There's a positive answer and a negative answer because it can be going left or right at its maximum speed. So those both make sense. They're just different directions. So the magnitude of Vmax is equal to square root k over m times the amplitude. What was square root of k over m? That was our omega, our angular frequency. So it turns out it's a really simple calculation to calculate the maximum speed if you know the amplitude and you know omega. So going back to our problem, write an equation for the maximum speed Vmax of the block. Well, that would be Vmax is equal to square root k over ma. Since k, m, and a are variables given to us, that's why I put it in those variables. And then you just put the numbers in. Last one, write an equation for the maximum acceleration. We haven't talked about acceleration at all, have we? But we know Newton's second law. Newton's second law says the sum of the forces equals ma. And if it is a simple harmonic oscillator, the sum of the forces is equal to, well, I'll put the minus sign here. The minus is for direction, kx. And so that means your acceleration is minus k over m times x. That's really simple. So what's my maximum acceleration? It just depends on what my maximum x is. So what do we call the maximum? X is the displacement, how far it's moved from equilibrium. What do we call the maximum displacement? Amplitude. Now I put A max, I left the minus sign in there, but obviously you could have a negative or a positive acceleration, it depends on direction, that's minus k over m times a, or if we prefer, minus omega squared a. So as you can see, if you know k and m and a, you know the maximum speed and the maximum acceleration very simply. Then you have, how is it changing over time? It's changing over time sinusoidally. So what I wrote here is a sine wave. So I have x is equal to a, the amplitude, the maximum displacement, sine of omega t. What's the speed function? There are two ways you can do this. One is if you know calculus. Randy, you have to do this on your homework. You're given an equation for x and you have to find the speed equation. Well, you just take the derivative with respect to time because speed is change in distance over change in time, or in calculus form, derivative of position with respect to time. Without calculus, what I do is I say, well, remember that speed, how does speed relate to the slope of a line? If I draw position versus time, go back to the second lab of the year, plus third lab of the year. We did both.
That's how steep it is.
How steep it is, the slope. So the slope is the speed. So if you look at this graph, this is the steepest positive slope right here. So it's going to be at maximum speed. Here you have a slope of 0. Here you have the steepest negative. It's going to be negative speed. Here it's 0. The speed as a function of time is going to look like this. It starts at maximum. That's a cosine curve. And so this is omega A cosine of omega t. So if you know the position equation, with calculus you take the derivative. Without calculus, notice I had to bring out the omega. I say bring out, without calculus you don't know what to bring out. But I have omega A, that's my maximum speed, times cosine of omega t. And then finally, acceleration. We just worked out an equation that said acceleration was equal to minus omega squared times the position. And so acceleration is equal to minus omega squared times the position. And there we have the equations for position, speed, and acceleration as a function of time. Now there's one more complication that can be thrown at you. And that is, you could have what we call a time offset, that it's not a straight sine wave where time equals 0, it's at position 0. And that's indicated by putting omega t plus some phase angle. And so if I just erase this here, plus phi, we use the Greek letter phi because that's the pH that phase starts with. And so there's the general forms of the equations. All right, that was a fun equation, right? Or a fun problem, right?
Super fun.
Yeah, I like doing physics problems. It gives me joy in life. Another problem. A grandfather clock uses a pendulum, i.e. this, with a period of 2 seconds. What's the period? What does it mean?
Period is the amount of time it takes to do one full.
Okay, the time it takes to do one full cycle. You remember Andy measured a lot of periods last class period. In one such clock, the pendulum bob has a mass of 150 grams. Is that important? Nope, that's not important. The pendulum is set into oscillation by displacing it 33 millimeters to one side. Is that important? It could be because we have to make sure it's a small angle if it's going to behave like a simple harmonic oscillator. So then we have the question, what is the length of the pendulum? Now this is a typical kind of physics problem. It doesn't give you any explanation of how to get there. It just gives you the facts, that's like Joe Friday, and asks you to find a conclusion. So how does the length of the pendulum relate to the information we have?
The triangle.
Do what?
The 0, wouldn't it be? You just said do a triangle and then figure it out.
What we have is period is equal to 1 over frequency, or 2 pi over omega. And we know that omega is equal to square root of g over L. for a pendulum. And so if we put those two together, period is equal to 2 pi square root L over G. Notice 1 over square root G over L is square root L over G. What are we trying to solve for? The length. So if I'm going to solve for the length, I'm going to have T times 2 pi is equal to square root L over G. Square both sides, as Randy would tell us if he was, And so I have L over G is equal to period squared times 2 squared times pi squared. L is equal to G period squared 4 pi squared. So now we can just put in numbers. My period was 2.0 seconds. Then I put that forward. And so we pop that in the calculator. Anybody?
I got 1,547.
Did I make some kind of goofy mistake? Because that's really long.
I made something.
No, I think I did because, I mean, you have 16 times pi squared times 9.8. I must have done some math wrong here. Omega is root G over O, 2 pi over omega. Yes. No, that's right. I definitely made a mistake somewhere here because it's less than a couple meters. Okay, let's test Richard's memory just a little. What are the units? Where are we on this? Okay, we're here. I said omega is equal to square root of G over L. That'd be square root of 9.80 meters per second squared over something in units of meters. Those are going to turn out to have the right units. So I'm pretty confident I remembered that correctly. And then omega is 2 pi F. F is equal to omega over 2 pi. Period is equal to 2 pi omega. That's where we started, right? It sure doesn't seem right, because they're not more than 2 meters long.
Oh, wait, did we multiply it by 2 pi instead of dividing by 2 pi?
Yes, that's where the problem is. Thank you. And when you say we, you're being very generous because you didn't make that mistake. There. Whew. I think I told you when I started teaching, they'd had a dentist teaching the year before me at PUC. And I went to him to have my dental work done, figuring, that's kind of cool. And he's talking about his teaching. He's like, yeah, I make mistakes in class all the time. I think it's good for students to see that even teachers can't do the problems. And then he said, yeah, for the test, since students can't do physics problems, and they're paying good money to go to school here, they deserve to get an A because they're paying good money. So the night before the exam, I would go over all the exam questions so they would know how to do them on the exam the next day. I was really concerned about the quality of my dental care after that. What was that? Yeah, I did. Okay, it's how much? Yeah, that's much more like it. 0.993 meters. So that's how long our pendulum is. By the way, we all make mistakes. I think you can understand that I make mistakes. You don't need to see them all the time. So it's 0.993 meters. Does this initial displacement satisfy the small angle approximation? Okay, now we can do trigonometry. What is the small angle approximation? If sine theta is approximately equal to theta. So we can use some trig, just cruising over here. Here's L. Here's what we call S, the arc length. And theta is equal to S over L. That's definition. If you have a complete circle, what's the angle? What's the angle for a complete circle? 360 degrees or 2 pi radians. And so you should have 2 pi radians equals, what's the length of a complete circle? What do we name that? Circumference. So we should have 2 pi radians is equal to the circumference over the radius, or 2 pi r over r. Yep. So now all we have to do is say theta is equal to, it was 33 millimeters, so 0.033 meters over 0.993. Yeah. And we get the angle, and then take the sine of that, making sure your calculator's in radians. If the number stays the same, then it's good. If the number changes, well, that tells you how much error you have. So I'm actually going to do that myself. First, change it into radians, because it would be ever so sad if we did it in degrees, because it just wouldn't work out. 0.033 divided by 0.993 is equal to, and then if I take the sine of that, so we look at that and we're like, 2.7, actually it was this, if I kept one more digit, it was 2.6. Is that close enough for us to say they're the same roughly? I'd say yes. You know, that's in the 1, 2, 3, 4, 5th decimal place, well, 5th significant digit. That's a very small error. So it's very good to say that it's a simple harmonic oscillator, because it's a good approximation. Any questions about that problem? Clear? Are we dead? Yeah. Oh, you're not supposed to answer that.
They literally died.
I got better. All right. Coming back to this energy, we did this energy calculation with the original purpose of being able to relate the amplitude to the maximum speed. But we can take the generic case for any old position. Our energy is equal to 1/2 kx squared plus 1/2 mv squared. And we can say this is equal to that or to that, and make an equation that solves v as a function of x. I'm not going to actually do the work right now because it really is pretty simple. Just realize that you can use the energy relationship to always find v as a function of x. Remember, this equation we started with was x is a function of time. But here we can find v as a function of x. Resonance. We must watch video. This video is actually, for some reason, the YouTube thing I've linked doesn't have audio. This comes from a science video that I used to have a copy of. This is the Tacoma Narrows Bridge, a bridge built between Seattle and Tacoma. It's in the Washington area anyway. And yeah, soon after it was built, they noticed that even with small amounts of wind, it had alarming motion. What do you suppose people my age did?
Drove on it anyway.
No, people my age drove long distances to go around that, to not go over it when it was doing this. But what did people your age do? They're like, yeah, we're there. Who needs to go to the mall on Saturday night when you can go to Galloping Gertie, as they call it? This is a picture on the day of its failure. A newspaper journalist, or maybe it's a radio, I don't know. He comes out because he's heard there's something going on. It's pretty alarming. He drives out there and he says, there's commentary. It wasn't until I was halfway across that I realized there was something dramatically wrong. I got out. I struggled to try to get to the edge. The motion of the bridge kept dropping me down to my knees. Finally, I crawled along the edge. My hands were bleeding, blah, blah, blah.
Why didn't you just drive?
Why wouldn't you just, yeah.
No, it's a good question. There's a good answer. The car was sliding across at the time he got out of it. He couldn't control the car. It's not sliding here because things are calmer now than they were, which is hard to believe. An engineer came out, and the engineer now is talking on the video about how he's measuring the motion and, very, very dry, like that's what's going on. And then it stops, just stops.
Yikes.
Yes, and then the journalist finishes right here by saying, with true catastrophe all around me, I think the thing that bothers me most is I have to go home tonight and tell my daughter that her dog is dead because he left the dog in the car. He tried to go back to get the car, or to get the dog, but
Who reports their dog in the car?
who drives out on the bridge when it's doing this stuff, okay? So this is an example of resonance. Now, if you go look on physics fora, you'll find people saying, no, that's not resonance. It's a different thing that's exactly resonance. The argument is based on what was causing what. But the simple fact is this was behaving like a harp. You have a harp. You have strings. You pluck those strings. What do the strings do? They vibrate. But they don't vibrate with any old frequency. They vibrate with a specific frequency. Remember, frequency is the number of times per second that it oscillates. And that depends on the tension of the string along with the density of the string and the length of the string. Those three things come together to give it its frequency. Oh, look, with sound. Okay, this is probably going to be the same video, but with sound. But when I watched it before, it played another one of a tsunami in Japan. And I was like, if it plays that, I'm just going to let it go. But it didn't play that, so we lose. Okay, so this is an example of what we call resonance, where you have a specific frequency where things will oscillate at. So if you take my pendulum has a single frequency that it oscillates at, right? Now, of course, it's not a perfect simple harmonic oscillator. If I make it really big, it'll change. But it has a specific frequency. How could I change the frequency it oscillates at for the pendulum? Mass didn't matter. Remember in that problem I point out, the mass doesn't matter here. Okay, push it. Let's imagine this is my niece. I usually take my niece and nephew to the park all the time when they were kids, and I would push them in the swing. When you push them in the swing, you don't sit here and read a book and go, right? Because then you're pushing them at random intervals, and on average, half the time you're pushing with them and half the time you're pushing against them. On average, you're doing a positive work if you're pushing with them, giving them more energy. You're doing a negative work if you're pushing against them. And so on average, you're giving them no energy, just making them bounce around. So you push them at the frequency that is oscillating, and then the oscillations get bigger and bigger. And that's what happened with that Tacoma Narrows Bridge. The vertical wires were essentially being plucked by the wind. Wind blowing on those wires goes around and it makes what's called Kármán vortices. Little eddies of air go flying off of them. And each time an eddy flies off, it plucks the string one way. And they alternate the direction, so the wind is just plucking the string back and forth. and the frequency of its plucking is proportional to the wind speed. And if that frequency is the same frequency as which the string would naturally vibrate, then the amplitude gets bigger and bigger. Now, of course, that happens with any bridge, but there's another problem here. You have the span of the bridge, the flat part, and it has different modes of oscillation. You can have a mode where it oscillates like this. It's called fundamental. Then you can have ones where it does like this. Or you can have all kinds of other things. You saw it had some tipping motions, different modes of oscillation, and each one has a different frequency that it'll oscillate at. And if you have the frequency at which the strings are vibrating matches the frequency at which the span can vibrate, then you have energy from the wind builds up on this, is transferred to the span, and the whole span does its crazy oscillation. And so that's what led to this failure. Now, this bridge was designed to be like the Golden Gate Bridge. The Golden Gate Bridge doesn't have any problems like this. And so engineers spent a lot of time analyzing this. And what they determined is, you notice that this is far narrower than the Golden Gate Bridge. And the dimensions, because it's narrower, it turned out that its frequencies were in a range that could resonate with the wires, whereas Golden Gate Bridge, with its wider bridge, doesn't have that problem, thankfully. And so this bridge was eventually rebuilt. It was built in a rush. It was during wartime to try to make it more efficient to transport munitions, I think, to ships or something like that. And so it was called Galloping Gertie because of its motion. And then they called the new one Sturdy Gertie because it didn't gallop anymore. Good to know, right? So let's get into this resonance. Talking about waves. A wave is a traveling oscillation. So the oscillations we talked about here, this was oscillating back and forth, covering the same position over and over and over. A wave is moving, not coming back to the same place over and over and over. So my favorite example of waves are ocean waves. Ocean waves most clearly move, and you can see why I was going to go ahead and play through the tsunami one, because that's where we're going next. Not to tsunamis, but to waves. So you had a homework problem that says you're sitting and you measure that in 4.2 seconds, 6 waves have come into shore. With that information, what do you know?
Well, in 4.2 seconds, 6 waves.
Yeah. So what was the time per wave?
4.2 divided by 6.
Yeah. 4.2 divided by 6 is the time per wave. And what's the name we give to that? The period. And you could just invert that to find the frequency. So this was a traveling oscillation, though. And so when we show a traveling wave, we now have a picture that instead of having time on the horizontal axis, we have position. So this is a different graph because we're looking at position versus time, or displacement versus position instead of displacement versus time. But if you look at this, it looks the same as what I drew before. And so before, we took the time from the peak to the next peak, and what did we call that time? Not the frequency. The time for it to repeat was called the period. Now it's not a time on that horizontal axis, it's a distance. And so this is the distance for the wave to repeat. And this distance we call the wavelength. So that what is that letter? Lambda. That's the Greek L. So L for length. Lambda is the wavelength, the length for it to repeat. Now, if the wave is traveling at some speed v, so we have v wave right there. If it's traveling at some speed v, what would we call the time that it takes for it to repeat? Time it takes to repeat is the
Period.
period. And so if I take the wave speed and multiply it by the time to repeat, what should I have? I should have the distance for it to repeat, right? But what do we call the distance for it to repeat? The wavelength. The wavelength is the distance for it to repeat. And so we often write this as V is equal to, well, we never write it this way. V is equal to wavelength over period, but since 1 over period is the frequency, the wave speed is equal to the frequency times the wavelength. So that's a fundamental relationship for any wave. If you know its frequency and its wavelength, you know how fast it's traveling. Or, well, any two, you know the third one. So let's just take something simple. This will work, except for I want it to be a sound wave. Sound waves are like this. Now we have two fundamental types of waves. I have my slinky all ready to go, but we only have 4 minutes left, so I'm not going to pull out the slinky. Just look at the pictures. Two fundamental types of waves we talk about. A longitudinal wave and a transverse wave. Longitudinal waves, well, let's talk about transverse first. Transverse is the one that I had here first because it's the easier one to talk about, generally speaking, but it's not the same thing as a sound wave. Transverse wave. It's transverse if the wave velocity is perpendicular to the displacement direction. So with a slinky, you're moving the slinky like this, so the displacement is vertical, but the wave is traveling horizontally. Those are perpendicular, that makes it a transverse wave. And what would you call this? Now keep in mind, this is a picture you take with the camera, so it's all at one time and positions on the horizontal axis. So what would you call that distance? That's the wavelength. What would you call that? Amplitude. Excellent. So that's a transverse wave. Examples of transverse waves. Light is a transverse wave. Longitudinal waves is when the motion of the particles is the same direction the wave is traveling. So in this case, the slinky is being pulled back and forth like this. So the motion of the pieces is horizontal and the wave is traveling horizontal. That's called a transverse wave. How would I specify the wavelength here?
The middle of one is the compressed to the middle of the next.
Right. Now the amplitude is going to be harder to determine here because the amplitude is how far that piece of the slinky has displaced from where it normally would be. And that's kind of hard to figure out looking at a picture like this. Sound is an example of a longitudinal wave. So let us say that I am humming a concert A. What is the frequency for a concert A? Isabel? Looking at you, Miss Music Theory 6 or however far you've taken.
I mean, she has perfect pitch. No.
Do you know the frequency of a concert A? No. 440 hertz. Now, different orchestras might tune a little bit higher or low of that, but that's the standard concert A. So if that's the frequency and the speed of sound is 342 meters per second in a room temperature room, then what is the wavelength of a concert A? You might recall I said if you know 2 of these, you know the third. Somebody want to quote what the equation is?
E equals lambda.
So if V is lambda F, then lambda is equal to V over F is equal to 342 meters per second over 440 hertz. Remember the units. What is hertz? 1 over S. So I'm going to put 1 over S so we see, yes, my seconds cancel, and I'm left with 0. What did you say, 77? So that's the wavelength of a concert A. So something like that. Okay, we are out of time. We will pick up here. Yes, you may keep the test. We pick up here on Monday.